Hello, welcome to Business Statistics. In this lecture, I will talk about P charts. Previously, we have discussed about X bar and R charts. So these charts are mostly used when we have variables that can be measurable. So that means they have magnitude. So examples of this would be if we are measuring length of a rod or something like that, or measuring the diameter of a ball, or gallons of water in a bottle. So these are all measurable units. However, P charts are used when we are talking about attributes. So attributes are characteristics of a product. For example, if we want to measure leakage in a container, we will use a P chart. Or if we want to determine how many determine the scratches, in a car paint, so that's a proportion. Or we wanted to determine number of defective transactions. Number of maybe wrong transactions. So these are some of the examples. So mostly the attributes are defined by defective or non-defective unit. So we can define them as defective or non-defective. So the other way we can say is conforming to a standard, conforming or non-conforming. So again, P charts are used to control the process. So we need the upper control limit and lower control limit for P charts. So we will have a lower control limit, which is represented by LCL. So the formula for lower control limit would be P minus 3 square root of P1 minus P divided by N. So here P is population proportion. So that is, we are assuming that the population proportion is known. So this is population proportion is known. So the other way we can say for population proportion is the standard. So they will specify the standards, like how much tolerance is allowed, or for example, this is standard percent defective. So mostly if there are standards for defective, then we can kind of say it's a population proportion. So similarly, the upper control limit UCL is P plus 3 times, that is 3 deviations, square root of P1 minus P divided by N. So here N is the sample size. So again, P is population proportion or the standard, and N is the sample size. So if population proportion is not known, so if this P is not known, then we will use the formula LCL is equal to P bar minus 3 square root of P bar 1 minus P bar divided by N. So the formula looks the same. So I will write the upper control limit also and then define what is P bar. So upper control limit is P bar plus 3 square root of P bar 1 minus P bar divided by N. So here N is the sample size again, and P bar is defined as number of defects found in all samples divided by total number of items in sample. So that's how we kind of define the upper and lower bound, and the center line in this case. So we have for a control chart, we have a upper control limit and lower control limit. So if the proportion is population proportion is known, the center line would be the population proportion, which is P. And the center line here in this case where P is unknown, population proportion is unknown. So this is the case of unknown population proportion. So in this case, the center line would be P bar. So this is the basic concept of P charts. Now we can solve a couple of problems by using P charts. So let's discuss the problem. So we have a quality inspector. So we have a quality department. And they are looking at so here is the department, and they are looking at the defective parts coming out of a production system. Defective products. So each day the department samples 200 units per day, and then the quality department has a standard where they say their standard is mostly the defectives are around 2%. So this is a standard given by the quality. So this is standard. So that means the population parameter P would be 2%, which is 0.02. So now the quality department measures each day how many defects are there. So we'll get this data set. So day 1. So this will be given for if you are solving problems. So number of defectives so day 2 day 3, day 4, day 5, so the number of defects that the company observes is out of 200 units on the first day, they observe 9. On the second day, they observe 7 defects. On the third, they observe 8 defects. On the fourth, 15 defects. And on the fifth day, 11 defects. So now we wanted to so if you see, we wanted to determine our upper control limit and lower control limit. So the formula for lower control limit, so since we are given a standard, we will use the known population proportion formula, which is P minus 3 times square root of P1 minus P divided by N. So the lower control limit for this problem will be 0.02, so P is 0.02 minus 3 times square root of 0.02, 1 minus 0.02 divided by N is 300 because we are sampling 300 per day. So 200, N is 200 because we are sampling 200 per day. So our lower control limit value would be negative 0.0097. Since we don't have negative defects, we will round it off to 0. So that is 0%. So now the upper control limit would be 0.02. So the formula, maybe I'll write the formula for upper control limit, which is P plus three square root of P1 minus P divided by N. So our upper control limit would be 0.02 plus 3 times square root of 0.02, 1 minus 0.02 divided by 200. So this is going to give us 0.0497, that is 4.97. So now to draw a P chart, we need percent defective here. So we will do percent defective. So to convert this 9 into percent, we will do 9 divided by So out of 200 samples, we have 9 defective. So 9 divided by 200 multiplied by 100, that is going to give us 4.5%. So similarly, we can do 7 divided by 200 multiplied by 100. So that gives us 3.5%. 8 divided by 200 multiplied by 100, that gives us 7.5%. And then 15 divided by 200 multiplied by 100, this is going to give us 7.5%. This is 4%. This is 8 divided by 200 is 4%. And then finally 11 divided by 200 multiplied by 100, I'm going to get 5.5%. So this is 5.5%. So we got these percentages. So now I can draw the P chart. So if I have this chart, and then we have day here, so this is day 1, day 2, day 3, day 4 and day 5. So now I will draw the lower control limit. So the lower control limit here, maybe I will use a different color. So this is lower control limit. So the lower control limit is 0%. So this is 0. And then upper control limit is 4.97%. So I will use this 4.97 and draw the upper control limit, 4.97. And then our center line would be P. So that is, P is, they gave us 2%, P is 0.02, so that's 2%. So then, so now we can plot each one of these. So 4.5% would lie somewhere here, 3.5% would lie somewhere here, and then so that is this point, and 4% would lie somewhere here, and then 7.5% would lie somewhere outside the control limit, and the fifth one is 5.5%. it will also lie outside the limit. So if you join these points, you see these 2 points are out of control, so the process is out of control. So that is how you use the known population variance. Suppose if we don't know the population variance, that means we are not given with this standard. Then how to do the same problem? So in that case, our formula changes to LCL, lower control limit, would be P bar minus 3 square root of P bar 1 minus P bar divided by n, and the upper control limit would be P bar plus 3 times square root of P bar 1 minus P bar divided by n. So we need P bar here in both the cases, so we will do P bar is mostly defined as total number of defects found in all samples. So that means we have to add all of these. So 9 plus 7 plus 8 plus 15 and plus 11. So that is 9 plus 7 is 16, 16 plus 8 is maybe, let me see, so 9 plus 7 16, 16 plus 8 24, 39, and then we have 50. So our P, the top of the numerator would be 50 and the denominator would be, we are taking 200 each day, so we have 5 days, so we will do 5 times 200. So this is going to give us 50 divided by 1000, that is 0.05. So let me erase this and rewrite it. So this is 0.05. To get this 50, we added all of these. And the total we got 50. So once we have the P bar, we can substitute P bar into our formula. So P bar would be 0.05 minus 3 square root of 0.05 1 minus 0.05 divided by n is 200. So that is, we are going to get the lower control limit as, if we calculate this, 0.05 0.0037. So this is our lower control limit. Similarly, we can calculate our upper control limit, which is 0.05 plus 3 square root of 0.05, 1 minus 0.05 divided by 200. So that is 0.0962. So again we can plot our graph. So this is in terms, this is upper control limit. So this is in terms of percent, it's 0.37%, and this is in terms of percentage, it is, this is 0.037. And then this is 9.62%. Okay, so once we have that, we can draw again our graph. So this is days. So this is day 1, day 2, day 3, day 4, day 5, and then we have our control limits. So our lower control limit is 0.037. This is 0.37, not 0.37, sorry. So I will kind of write here, this is 0.37%. So our lower control limit, LCL, this is 0.37%. And then our upper control limit, UCL, is 9.62%. And then our center line, which is P bar in this case, is 5%. So that is 0.05. So this can be written as 5%. So this is 5%. So now I can again plot these values. So 4.5, 3.5, 4, 7.5, 5.5, we can again plot. So 4.5 would lie somewhere here, and then 3.5 would lie somewhere here, 4 would lie somewhere here, and then 7.5 would lie somewhere here, and 5.5 would lie somewhere here. Now if you see, the process is in control. So if we are using if the population variance is unknown, the process is in control. So this concludes our lecture on P chart. Thank you.